Hey, one and all, welcome to the HESA e-library, also called the HESA video bank. This video is being made to explain concepts regarding chemical kinetics. The only caution here is that this is a supplementary material, not an alternate material to what we are doing in class. Now we start chemical kinetics. So we are saying is the study and discussion of chemical reaction with respect to the reaction rates, effects of various variables, rearrangement of atoms, formation of intermediates, etc. So we'll talk about all these with respect to this topic. Now, the study can happen at different levels. The first level is the macroscopic level, where we study the amount reacted, the amount formed, and the rates of their formation. We can look at the same chemical kinetic at the microscopic or molecular level, where we look at how the atoms and molecules collide to form products in the chemical reaction. Now, we are saying that molecules, before they can form products, will need to have at least a minimum energy called the activation energy, right? Now, reaction rates. Reaction rate is the first concept that we will discuss. The reaction rate is the change in concentration or amount of either the reactant or product. Now, along a series of chemical reactions, this is what will happen. The reactants will decrease, and then the product will increase. And so if you are measuring how fast the reactants are decreasing respect to time, or how fast the products are appearing or increasing respect to time, call it the reaction rate. Now, if you are looking at amounts, this will be the unit that we'll have. We can have mole per second, we can have gram per second, and it goes like that. If we are looking at concentration, we can have the concentrations per second, like we have mole per liter per second, we can have gram per liter per second, we can have percentage per second, right? Now, respect to reaction rates, we have average rates. Average rate would be the total rate for the course of reaction, the average, right? The mean rate for the course of a chemical reaction. We can have instantaneous rates, that is the rate at any instant along the reaction pathway, right? And then we can have initial rates, that would be the rate at the beginning of the chemical reaction. Now, factors that influence reaction rates. The first is the nature of reactants. We have different points. Acid-base reactions are usually fast reactions. Reactions that leads to the formation of salts or exchange, just exchange of ions are all fast reactions. Now, reactions that involve large molecules are slow reactions, or that require these large molecules to be broken apart, right? Yes, now reactions that require breaking of strong covalent bonds are also very slow reactions. Temperature. Now, generally, temperature increases the rate of reaction. So the higher the temperature, the faster the reaction, right? Now, the idea is that higher temperatures, reactant molecules have high kinetic energy. They move faster, and then they collide more often. So the frequency of collision and the energy of collision is increased. Two important factor, right? Now, we say the effect of temperature is discussed on the effect of activation energy. Now, what temperature does is it doesn't really decrease or increase that activation energy, right? But what it does is that it gives the molecule more energy and then higher frequency of collision so that they can cross the activation energy, right? That is the idea here. Now, effect of concentration. I'm saying as concentration of reactants increase, so does the likelihood of the reactant molecules to collide. Now, when we add more particles to the solution, right, that's when we increase the concentration, the probability of the reactants colliding increases, right? And that will increase the probability of products forming. So the rate of reaction is increased by concentration. Now, the dependence of rate of reaction on concentration is discussed under rate laws. The rate laws will be the next thing that we'll talk about after the rate of reactions, right? Now, rate laws are expressions of rate in terms of concentration. So rate laws will just show you how the rate of a reaction depends on the concentration of the reactants. And we are looking at reactants. Unlike the rate of reaction, which can be expressed in terms of the reactants and products, rate law is expressed in terms of only the reactants. Very important to note, right? Now, the following is a brief summary of the topics regarding rate law. The rate law can either be differential and integrated, For the integrated one, we have first order, second order. Now, real law relates to homogeneous reactions. We are saying that for heterogeneous reactions, reactants will be present in more than one phase, right? And then for heterogeneous reaction, the rates are affected by surface area. So heterogeneous means the phase is like we have liquid, solid, and gas being in a mixture, or just maybe liquid and solid, maybe solid and gas. And the rate is affected by the surface area. And we know that the higher the surface area, the higher the chance of pollution, right? So the faster the reaction. So gases definitely would have higher surface area and then faster rates relative to liquid. Then the last of them will be solids. Then catalysts. Right now, catalysts are generally used to speed up chemical reactions. So in the presence of a catalyst, reaction rates are faster. Now, how catalysts work, they change the reaction mechanism, right? Now, the new mechanism that the reaction will undergo would have a lower activation energy. So that will enable more of the reactants to form products, to have their required energy to form products. Kinetics studies the rate at which chemical processes occurs. Beside information about how the speed of reaction we have already mentioned, the share slides on also the mechanism of reaction. Now, this is a summary of everything that we'll talk about in this topic. Reaction rate, we have started already, shows us or helps us to measure rates, right? How fast the reaction is proceeding. Now, if you look at the real laws, it helps us measure how the concentration of reactants affects the rates, or how the amount of reactants affect the rate of reaction, right? Now, if we look at the integrated rate laws, they help us to calculate the amount left or the time taken to reach a particular amount, right? Half-life is the time taken for half of the reactant to decompose or react. Now, the Arrhenius equation will show us how the rate constant changes with temperature. Now, this is something very important to note. The rate constant is a constant for a reaction, but the reaction should happen at a particular temperature because a change in temperature would affect the rate constant Q. Now, mechanism of reaction, we'll also talk about mechanisms, right? The link between the rate and molecular scale processes. Confidence building question 1. What drives chemical reaction? The answer is activation energy. Activation energy is the minimum energy you require for a reaction to proceed. Reaction rate. The rate of reaction can be determined by monitoring the change in concentration of either the reactant or product as a function of time. We have talked about this already. So in summary, the reaction rate is just changing the reactants over changing time, right? Now, if you are looking at the reactant, we are looking at how the reactant decrease with time. If we are looking at the product, we are looking at how the product appears or increases with time. Now, what we have been given is a very simple table of time against concentration, right? Time against concentration. Now, we are saying in this reaction, the concentration of butyl chloride was measured at various times. So that is what we have, right? Now, the average rate of the reaction over each interval is the change in the reaction in the concentration divided by the time. So if I want for me to get the 1.9 times 10 raised upon -4, what I do is that I find the difference between the concentration here and then the difference between the time here. Difference between the concentration here and the difference between the time here. So the change in concentration over change in time will give me this rate. Right? The change in this concentration over the change in this time will give me this rate. So that's what has been done here, right? Now we are saying note that the average rate decreases as the reaction proceeds. Now, the reason for this one is because as the reaction goes on, fewer molecules are left as reactants. And so the frequency of collision decreases. You realize that the rate is decreasing. One thing you have to appreciate that the rate is decreasing. And the reason why the rate is decreasing is because as the reaction is proceeding, as more reactants collide to form products, the amount of reactants reduces. And so the frequency of collision also reduces. That is what we are looking at this point. Now, we're saying a plot of concentration versus time would give us a curve right? A curve like this. Now, if we draw a tangent to the curve and then we find the slope there, right? It gives us the instantaneous rate. So that gives us the instantaneous rate of reaction. Instantaneous rate of reaction. The change in concentration over change in time can be represented as D, that's D of concentration over the T, right? So that's differential. This is differential rate. Differential rate. Now, we are seeing that the reaction slows down with time because the concentration of the reactant decreases. We have already talked about that, right? Now, in this reaction, the ratio of the C4H9Cl to the C4H9OH is 1:1, right? That is the appearance of the butyl chloride is the same. Sorry, the disappearance of the butyl chloride is the same as the appearance of the butanol, And so if we are expressing the rates, right, we are just looking at the decrease. That's why we have a negative sign here. The decrease in the concentration of the butyl chloride over time. And then it should be equal to the increase, the appearance of the butanol over time, right? Now, if the ratio of the reactant to the product is not 1:1, as we had in the other example, like we have in this case. Now, what we have here is H2 plus I2 reacting to form 2HI, right? That is, for every 1 molecule of hydrogen gas that disappears, we have 2 moles of what? HI that appears. And so for us to get a uniform constant rate, single rate, or homogeneous rate for the whole reaction. Now, we first of all state the rate of reaction, which is normal, this one, the disappearance of the concentration of the hydrogen gas over time. But then when we get to the product, it is the appearance of the product over time, all right, but we divide it by 2 so that we can get a uniform rate of reaction for the whole reaction pathway. That is that for that. Very simple, right? So it just shows that if I have, let's say, A reacting to form 3 of B. Now, what is happening is that when 1 mole of A disappears, 3 moles of B appears. And so the rate of reaction, the differential rate will be equal to negative D of concentration of A. That's in terms of the reactant over dt. But then if we are looking at the same rate in terms of the product, it is still the appearance, the positive of the differential in B, the appearance in B over T. But then we have to divide it by 3. We divide this by 3 to get a single homogeneous rate for the whole reaction pathway, right? Good. So that is that for that. There's another reaction here. We say the stoichiometric coefficient of species B is twice that of A. That is, the concentration of B will decline twice as fast as that of species A. Similarly, the concentration of C increases 3 times as fast as the decrease in concentration of A. Now, if you are supposed to state the rate laws for, conceptually, there should be a single unambiguous rate for a reaction. And so if we are supposed to state the rate law, right, for that reaction, we would get this, right? So the disappearance in A, then the disappearance in B divided by 2, then the appearance in C, because C is the product, divided by 3, divided by 3. That is how we look at it. Now, there have been concepts that we have redefined the rate of reaction, the differential rate of reaction. We are seeing that it is the slope of the concentration time plots for species divided by their stoichiometric coefficient. So now this is a complete definition for rate of reaction, right? That is slope of the concentration time plot of a species divided by the stoichiometric coefficient of that species. And that is what has been shown here. That is what has been demonstrated here. The negative is put in front of the reactant to show that they are disappearing, and then positive for the product to show that they are appear. But now to generalize, right? Always the rate of reaction will be the change in the concentration of the reactant as we have here, right? Divided by the change in time. Now we have to always divide by their stoichiometric coefficients, right? So that is what has been demonstrated at this side. That is it for differential rates. That's rate of reaction. Rate of reaction. Now, let's look at the Reed's law. We have already said that the Reed law will show us how concentration affects the rate of reaction, right? And so we are saying Reed law is a mathematical relation determined experimentally, very important, experimentally to describe the progress of a chemical reaction. To determine the Reed law, the rate at different starting concentration is measured. Now, this is one way of determining the Reed law. We have different experiments. So this one has different experiments. We have like 8 different experiments. Now we have different initial concentrations, and then we look at how they affect the initial rate of reaction, right? And then so for the first experiment, we have 0.01 molar of the ammonium ion, and then the NO2 minus ion, we have 0.2 of it, and then this is the rate. Now, for us to be able to determine the effect of a single factor on the rate, we have to make sure in 2 experiments, we compare 2 experiments, and the 2 experiments we are comparing, the other factor is maintained constant. So assuming I want to find the effects or the order for the ammonium, I have to make sure the NO2 minus is constant. So if I look at experiment 1 and 2, now the concentration of this one was maintained, but then the concentration of the ammonium has increased by 2, right? Now we have to look at what has happened to the rate. The rate has also increased by 2. That is something that we can live by. Now, if you look at between equation 1 and 3, the concentration increased by 4. Now the rate, and this one was constant, right? The rate has also increased approximately by 4. So you realize that if I increase the concentration by 2, the rate also increased by 2. So if I'm writing an expression, rate is directly proportional to the concentration of ammonium ion, right? Now the power of ammonium ion here will be 1, such that if I put 2 here, right, 2 raised to the power 1 will still be 2, so that the rate itself would also be affected by just the 2. And that is what we have observed here. Whatever increase that we apply to the ammonium ion, the same increase affects what the rate of reaction. And that shows that the power here, the exponent is 1. And so we say that respect to the ammonium ion, the order of reaction is what? Is 1. Now, in the same vein, if we want to find how the NO2 minus affect the rate of reaction, right? We have to make sure the ammonium is constant. And so these series of reactions, experiments 5 to 8, the ammonium has been maintained. If you look at experiment 5 and 6, the ammonium was maintained. Now the NO2, right, the nitrous ion, has been multiplied by 2. Now the rate has also been approximately multiplied by 2. That is to show that respect to the nitrous ion here, the rate is also what? A first order. The rate is a first order. The rate is a first order. That is R directly proportional to NO2 minus. The rate, the power here is raised to the power 1, such that if I multiply this by 2, if I multiply this by 2, the net effect on the rate still becomes 2, because 2 raised to the power 1 is still 2. That is what has happened here. Now, there are other instances where you realize that when you multiply, when you maintain one of the species and you multiply the other by 2, it does not affect the rate, right? It does not affect the rate. That will show you that if the rate is directly proportional to, let's say, concentration of A, and I multiply this by 2 and it doesn't affect, it means it's raised to the power 0, because anything raised to the power 0 is 1. So it doesn't really have any effect. It doesn't have any effect on the rate. So in a case where we see that multiplying the concentration by 2 and then the rate is not affected, that means we are looking at a 0 order reaction. The only other one that we can have is when we have a rate, right? Like rate the power can be 2. We call it second order. Second order. Now, what will happen is that if I multiply the concentration by 2, you realize that the effects will be by 4. So an exponential increase. Effect will be by 4. The effect will be by 4. And that shows the second order reaction. We'll come across some of these examples. The truth is that rate of reaction can, that's per calculation, we can get decimals, we can even get negative answers, right? Yes, sometimes we don't get positive, but the most common one will be 0 order, the first order, and second order. And for our calculation to be simple, usually we do approximation when we get decimals, right? So that's that for that. The method that I use here is called inspection. So I just apply the inspection method to find my rate of reaction. Very simple. We move on. So we have what I've explained is here. When the ammonium is doubled, you realize that the rate doubles, right? Likewise, in experiment 5.6, when the nitrous ion is doubled, the initial rate doubles. And so if we are looking at the rate of reaction, the rate is directly proportional to the concentration of the ammonium raised to the power 1. So it's directly proportional to the nitrous ion raised to the power 1. If we combine the rates, it's directly proportional to the ammonium ion raised to the power 1 and nitrous ion raised to the power 1. Now, if we change the proportionality sign to an equal sign, we introduce a constant. This constant is called the rate constant. I've already talked about the rate constant, that it is constant at a constant temperature. Now, this is what we call the rate law, because it's showing how the rate depends on the concentration of the reactant. How the rate depends on the concentration of the reactant. Now, there are two forms of rate laws. We have the differential rate law, and then we have the integrated rate law. The differential rate law relates the rate of reaction to the concentration of various species in the system. Right? A rate law shows the relationship between the rate of reaction and concentration of species. If we have a gas phase, then we use the pressure of the species instead of the concentration. Right? Now, K is constant. That has a specific value for each reaction. The value of K is determined experimentally. So only through experiments we can determine the value of K. Right? Now, K is constant, but then K changes with temperature. So K is actually constant at constant temperature. Now, the unit of K changes, right? The unit of K changes. So for any reaction, you have to determine the specific unit of K. But then the rate is measured in mole per liter per second, and then concentration is measured in mole per liter. For zero order reactions, right? For zero order reactions, the rate is equal to the constant, right? The rate is equal to the constant. And so the rate is constant, and then the unit of rate here will be the same as the unit for K. And so the unit for K will be mole per liter per second. The first order reaction. Now for first order reaction, this is what we will have. The rate is equal to K, concentration of A raised to the power 1. Now for that, we can derive the unit. Deriving the unit is very simple. We can just keep in our head if we cannot derive it as per second, because every first order reaction, the unit of K will be per second, will be like that. Now, if we want to determine the unit of K, we can divide the side by the concentration of A, divide the side by concentration of A. Realize that K will be equal to the R over concentration of A, right? Now the K will be equal to the R. The unit of R is mole per liter per second. The unit for A is mole per liter. So you realize that the mole per liter here can cancel the mole per liter here, so that the K would be equal to per second. That is why we have the unit happening like that. Now I really lost second order reaction. So this is the differential rate law for second order reaction. Now R is equal to K, concentration of A raised to the power 2. So that shows second order. There's another way of writing second order. Right? This with respect to a single specific second order reaction. And then if you do the determination, you realize that the value, the unit of K is liter per mole per second, right? You can keep this one if you cannot derive it. The derivation is very simple. Now, rate law. So for this general rate law, we can define the rate as applies to every species here, and then we can define the overall rate. Now, this rate of reaction is first order respect to the ammonium, first order respect to the nitrous ion, but then overall we add 1 plus 1, the one here and the one here there. And then we'll get 2. So overall, the rate is what? A second order. Rate is a second order overall. Now, this is a graphical representation of the rate law. If it's 0 order, it means the rate is constant, right? So this is the horizontal green line. Constant, it won't change. The rate is constant as we can have here, right? As you can see here. Now, if it's first order, it means a proportional increase in concentration will lead to an equivalent increase in what? Rate. And so we have a straight line like this. And then if it is second order, then it's an exponential increase. So it's like a quadratic graph. It's an exponential increase with an increase in concentration. There's an exponential increase in the rate. That is why we have the curve. That's why we have the curve like this. Right, that is that for that. Now, confidence building question. They are asking us to write the rate law for reaction between A and B, where A is first order and B second order. If they give us such a simple question, this is how we have to write it. The rate will be equal to K, right? Now, concentration of A, they said it's first order, so raise to the power 1. Concentration of B, second order, so raise to the power 2, right? Now, for us to find the unit of K, which is the second one, this is everything about the first question. You have to divide this by A raised to the power 1, then B raised to the power 2, right? This is a way of making K the subject. Do the same thing at this end. A raised to the power 1, B raised to the power 2. B raised to the power 2. Right, so this will cancel this. And I'll have K being equal to the rate. Now the rate is measured in mole per liter per second. Then this side, we have mole per liter. Then this side, we have mole per liter all squared. So this will cancel this out. I would have K and being equal to, if I bring the squared out, I would have per second over mole squared, then per liter squared. That is because of the square affecting these two entities. Now, if I'm supposed to simplify it, I would have liter squared. That's if I'm bringing this up here, the negative will become positive and the positive will become negative. So liter square per mole squared per second. So this will be the unit of K in this overall third order reaction. Very simple. Now, confidence building question 4. We have this reaction, and then we are asked to determine the initial, we are supposed to determine K. Now, before we can determine K, we have to first of all find the rate law, the differential real law. Once we are done finding the differential real law, then we can find the value of K. Then we can find the value of K. So let's try this question quickly. For us to determine how the rate varies with respect to A, right, we have to make sure the other two are constant. So in equation 1 and 2, you realize that these two are constants, right? Now, when you multiply A by 2, right, from 1.1 to 0.2, the rate also multiplies by 2. That means it is first order respect to the first reactants. Now, for us to find B, we have to make sure C and A are constant. So if you look at equation 1 and 3, equation 1 and equation 3, you realize that A and C are constant. So we can look at the effect of B alone. Now, when we multiply B by 2, the rate is multiplied by 4. That shows that it is second order. It's a second order. Second order, that's an exponential increase, right? Now, for us to find the effect of C, the A and B should be maintained, right? Reaction where A and B is maintained. If we want a reaction where A and B is maintained, reaction 1 and 4, reaction 1, realize that A and B are maintained, the concentrations are the same, but then we have increased the C by 2. Now, when we increase the C by 2, the rate didn't change. The rate didn't change, right? That means with respect to C, it's a 0 order reaction. If I'm writing my rate law, my rate law is equal to K concentration of A raised to the power 1, concentration of B raised to the power 2, concentration of C raised to the power 0. So you can even omit it. So finally, I'll have rate is equal to K concentration of A raised to the power 1, concentration of B raised to the power 2, right? Yes. Now, this will be equal to the question that we solved up there. So we'll get liter squared per mole squared per second. This is what we'll get if you make K the subject and then cancel out the units. Very simple. Very, very simple. Confidence building question 5. We are saying if a reaction has an order of 3, write 3 rate laws that can be used to describe the order. So let's quickly attempt this question. Very simple. Now, for the question to be very easy, we can assume a reaction that has 3 reactants, right? Maybe to form D, something like this. We are only concerned with reactant when we are talking about Rayleigh law. Now, for the first overall reaction, that will give me an order of 3. I can say the rate is equal to concentration of A raised to the power 1, concentration of B raised to the power 2. Right? This 1 plus 2 will give me 3, so the overall is 3 here. I can have the rate concentration of A raised to the power 2, concentration of B raised to the power 1. Now, this is very different from the first one. And the overall, the 2 plus 1 will give me 3, right? Now, I can have the rates in equal to K, concentration of A raised to the power 1, concentration of B raised to the power 1, concentration of C raised to the power 1, right? And so 1 plus 1 plus 1 will give me 3. So these are the 3 ways of stating or writing the Rayleigh law for the overall order of reaction to become what? To become 3. Very simple for us to take note of. Good. Now, the next subtopic that we have to discuss will be integrated Rayleigh law, but that will be captured in another video. And so part 2 will talk about that. Thank you very much. If you have any question, kindly see any member of the SR Academy.